First, I will finish something we started long ago about finite quotients. This is just one of the examples of what we can do, we can do finite quotients geometrically, just take a finite quotient topologically, but this is not algebraic. There's no algebraic structure on this quotient. On the other hand, we can take the space of invariant functions, the ring of invariant functions. This will give you some ring, but you have to show that the corresponding algebraic variety is a quotient in the geometric sense. Okay, there was this stuff about finite morphisms. What we need today is that x to y finite morphism if or x. So if you have map from x to y, you have the map of rings from y to ox is finitely generated OY model. And you have two nice theorems that, well, it's if f from x to y is finite, pre-image of y is finite for all y in the big Y. And another, also, it's non-if, in addition to that, f is dominant. Then this map is not on, this pre-image is not only finite but non-empty. So f from x to y is surjective. If you have any questions about this, please ask. If not, I will go on because we had that like 2 or 3 times already. No questions?
So the theorem says that like the dominant finite morphism is surjective.
Yeah. Pre-image of any point is non-empty. Not only finite but non-empty. Without dominance, it's just wrong. As we have an example of finite of an embedding, for closed embedding, which is a finite map. Okay.
But it does work like the other way around. But if every fiber is finite, that doesn't apply.
No. There is an easy example. So you have a map from like c squared without a point to, well, without a point, it's bad, without a line, to c squared. This is definitely not finite because this is not finitely generated. It's generated by the so line f is equal 0 by f minus 1 power n. This is the generators for all n of this ring over this ring. So it's generators. It's infinitely many. And of course, you can't find finitely many generators because you can't express these guys through this for any finite number of generators over this ring. On the hand, you can have like union c squared without line, f is equal 0, and then you have a line, f is equal 0. Just disconnected union. This is mapped to c squared surjectively, but clearly not finite because it's not finite on each component. You can do the same with when you have just one component, when you have a non-irreducible manifold. It's not variety, it's not hard. But I will not do it now. It's an exercise. Or maybe I can. Why not? Okay, let's do it for a non-irreducible case. So you have a map C without 0, or just C, mapped to C. T goes to T squared. This is a double cover. Okay, and let's remove this 1, just a point. This is still a affine variety, this is a affine variety, and the preimage of each point is non-empty because the preimage of 1 is plus minus 1. 1 we removed, but the rest is there. On the other hand, it's not finite because you have 1 over x minus 1 power n. This is what generates this over this. And also x. So these are generators, but there are like infinitely many of them, and you cannot, there's no way you can find finitely many. It's easy to see because if you have finitely many, then the pole is bounded by the biggest pole in your set of generators. But the pole of this function in that ring can be anything. Okay. So this was the dominant finite morphisms. So surjectivity is not enough for finiteness. Finiteness is more strong condition. Thank you very much for this question. Okay, now find quotients. This is something we have seen a couple of times. So you have things like c squared, quotient by plus minus 1. And the invariant functions like plus minus 1 invariant functions are just even functions. This is the definition of even function. Even function is a function which is invariant under involution x goes to minus x. And we know what are even polynomials. So it's polynomials of sum of monomials of even degree. So it's generated, it's not hard to see that it's generated by x squared, y squared, and xy. There is a relation, and there is a theorem which we proved. I'm not going to repeat its proof. It was sort of complicated theorem that for each finite group G acting on a finitely generated ring. When I say acting, this means that it acts by automorphism. R, this ring Rg of G invariance is finitely generated. The important thing that this is in fact more or less universal construction. We shall see that more or less up to some birational stuff, every algebraic variety is obtained, well, every morphism is obtained as finite quotient. And, well, we shall see today, for instance, that every x admits a finite map to Cn. But what we shall see like next or a couple of lectures, that every finite map is in fact has this form. It's a group quotient. So this construction is not only important, it's sort of universal. Okay. So this was something we did last time. Maybe I should write a definition. Okay. So definition. If you have X algebraic variety, affine variety variety, which is equal to spectrum of a ring R, X quotient, and Gx acts on X. Action on a variety is the same as action on a ring because they have equivalence of categories. The quotient X over G is the same as spectrum of R power G, the invariant ring, and it makes sense by this theorem. Okay, today I wanted to discuss the points. So what are points of, so there are a couple of examples in this slide. One of the examples is there. Another example is even simpler. It is related to that map. So you have x goes to epsilon x, where epsilon is a root of unity. And root of unity is called primitive. The group of roots of unity is cyclic, and it is primitive, it's generator. So it's primitive root of nth power of 1, of primitive root of unity. Am I clear with this? Good. Then polynomial P is, let's call it the group generated by this G. G invariant if and only if P is a sum. Yeah, it's group of root of unities. So G is generated by epsilon. P is a sum from I equals 0 to n k, a n, a k, t power n k, or n I, a I, right? Why this is so? This is because if you have t power n, t power k, you multiply t by epsilon, you will obtain epsilon power k, t power k. And since this root is primitive, this is 1 if and only if k is divisible by n. So the only invariant under this map polynomials are these polynomials, but this is again a ring of polynomials. This means that the quotient with this G, the quotient C by G is just C. And this is this kind of map. This is like n-sheeted cover of C by itself. Okay. Am I clear so far? Now let's classify the points. The proof that there are precisely as many points as, algebraically points are maximal ideals. Geometrically points are orbits. We need to prove that they're the same. So theorem. We have G finite group acting on X, which is spec R, a fine variety. Yeah.
Of this action. So,
yeah.
So when we consider this cover, it will be a branch point, no?
Yeah, yeah.
So it's not a cover.
It's branch cover. Okay, acting on X, spec affine variety, and then we take RG, ring of invariants. Then maximal ideals in RG are the same as G orbits of G action. Of G action on X. So in that case that you mentioned, there's just one orbit which corresponds to 0 where action is trivial. But it is still the quotient. Okay, this is how geometry corresponds to algebra for the quotient maps. Okay, so let's prove it. Step 1. If you have a maximal ideal of R, so X is G invariant maximal ideal. Okay, so let's recall how you have a map from X to Y. You have the corresponding ring, say B, and this is say A, and this is mapped onto opposite direction. Then if you have a maximal ideal here, you take its preimage. Well, if it was like a dominant map, this would be just intersection with B, otherwise it will be preimage. So this is F star, this is F. You have here F star of M. Generally speaking, it will be prime ideal. This is why people usually work with prime spectra, not the spectrum of maximal ideals, spectra of prime ideals. But in our case, a maximal ideal is precisely the ideal where the quotient is C. So you can work with maximal as well. Okay, so you have a maximal ideal. You are interested in its image. Its image is a G invariant ideal, well, in invariant rings. If you have two ideals, M1 and M2, so what is this ideal? This is M intersected with RG, because in our case the map is dominant. There's no kernel. Then M and M2, if they belong to the same orbit, you take their intersection, doesn't change because this is invariant. M1 intersected with RG is equal to M2 intersected with RG. This is why if you have 2 points which are related by the group action, they're mapped to the same point. This is trivial. Okay, so now we should go back. We want to prove that if you have, we just proved that if 2 points are mapped to, if the 2 points are group related, they're mapped to the same point. Let's prove converse. You have an ideal, so it remains to prove. If you have a maximal ideal, is it M here? M inside the invariant ring, the ring of invariance. You could take its preimages, F minus 1 of M, which are different ideals such that their intersection with invariant rings is M. Is contained in G orbit. So if you have two ideals which are both preimages, they're both they're related by group action. Okay, the important thing is something we proved when we proved this Noether theorem here. Which it was a theorem about ideals. So if you have M inside RG, then you can take the corresponding ideal and then take invariance. So you take MR. This is an ideal in R corresponding to that. you take invariance here, and this will be the same as M. It's like you can lift ideals, and you can take, for each ideal, you can take invariance. Okay, and where we could be interested in, yeah, now you have the quotient ring, and you can describe the quotient ring, I mean the invariance in quotient rings in terms of the quotient of invariance. So you have invariant part. This because now I'm applying to, I have A, which is R quotient by M R. This is a ring, and I'm looking at it invariant ring. I use that, I just apply invariance here, and I obtain that it's RG quotient by M. But generally, it's a certain ring which is not, I mean, this is not a maximal ideal anymore. So the ring is, what we know about this ring, that it is, yeah, and also you have certain relation with respect to yeah. Anyway, so we have this. Now let's go further, and if you have maximal ideal in step 3, maximal ideals in F in A quotient in A, which is R quotient by MR, is the same as just the same as maximal ideals points in F minus 1 of the corresponding point. It's the same as maximal ideals in R containing MR. This by definition. If you have a maximal ideal in the ring R, you want to see what maximal ideals it corresponds to in the invariant ring. This will be all, I mean, sorry, if you have a maximal ideal invariant ring, you want to see what maximal ideals it gives in M. This will be precisely the ideal, maximal ideals in the quotient ring, because this would be ideals which contain MR and R maximal. Okay, so this is what we need to show is that there is an action of our group on this ring which acts transitively on the maximal ideals. And then they are done. So need to show that G acts on A transitively on maximal ideals. That's all, because the maximal ideals in this quotient ring are precisely the ideals which, after intersection with AG, become our ideal. Okay, so the last step, step 4, is that in fact we have a structure theorem for such rings. I mean, this is so this ring is finitely dimensional over C. Is it actually explained here? Sorry. It's not explained here, but it's not hard. It's left for you as an exercise. Yeah, this is why. Let me explain just in saying that. So you have R mapped to RG. Oh, sorry, converse. The spectrum X here, and the map is here, but this is a finite extension of that, in the sense that R is finite, finitely generated over RG. This is something we proved. And then this implies, in particular, that this model A is a finitely generated model over its invariant ring. So, and invariant ring of A is it's just C. It's a quotient of invariant by this. So the invariant part is just C, because M is maximal ideal. And A is finite over that, so it's Artinian algebra. And if you take quotient A by nil radical, it will be direct sum of copies of C. Generally, it will be direct sum of algebraic extensions, of finite extensions of our base ring, but our base ring is C. So it's just several copies of C. Okay, and obviously maximal ideals are the same, one-to-one correspondence to summands in this direct sum. Clear? Okay, now Gx, since this is true, G acts on summands transitively. Let me explain. Suppose it doesn't act transitively. If not, you have two summands, like C1, C2. They are not distinguishable by the section. Then you have invariant. Just take you have co-invariant, because you can have a map from your A to C, which takes two elements in C1 and C2, adds them together. So adds elements lambda. I mean, this is C and this is C. So you have copies of each complex number here in C1 and C2. This gives you a co-invariant. Then you have an invariant, which is so the standard co-invariant is, it should be unique because of that. It's just sum of all of the of all lambdas in all these copies. This is the only co-invariant you a priori could have. Co-invariant, I remind you, is a map to something which is invariant under group. But here you have an extra co-invariant. This contradicts to the invariant space being C. So this is just a trivial statement about group action. If you have a group action on direct sum of several copies of a one-dimensional space, it exchanges these copies in a canonical way. If the action is non-transitive, then you have additional invariants. So your group acts on C, on copies, exchanging the copies, because it maps unit to unit, idempotence to idempotence. And if somehow it fixes, it doesn't distinguish between two copies, you would have co-invariant difference between them, for instance, which is invariant under your group action. And this can't happen, because the invariant is unique. Was that clear? Please ask questions. Yes.
You mean, I think you actually mean the action in A quotient AG is.
The action on the set of summands. There is a finite set here, which is a set of C in the direct sum, or of maximal ideals.
I mean, AG is obviously preserved by the action of G, like AG.
AG is C.
It is preserved by the action of G.
The action is trivial, yeah.
So, I mean, in that step 4, you mean A content AG,
By nil radical.
but AG is in the numerical.
No, it's no. Nil radical could be something. Could be 0, could be non-zero. We didn't prove it. So I take a quotient of A by its nil radical, and it is direct sum of copies of C. We don't know anything about nil radical, and we don't even care. A priori, who knows? We didn't prove there's no nil radical. I think there is none, in fact. I think it's possible to prove, at least in finite, in zero characteristic. But we didn't prove it. Any more questions? Please ask. Okay, so we finished by proving that if you have you have this ring of invariants, you have an ideal. Its preimage is ideals in that Artinian ring A. Maximal ideals on Artinian ring A. A is direct sum of C, but they are group acting on C transitive, on copies of C transitive, so there is no the action on ideals is also transitive. Yes, please. Why it is reduced? Of course, if it is reduced, it would be 0. But this is the same. But I mean, this is a quotient ring. We didn't prove it is reduced, and quotient rings are typically non-reduced. So. Okay. So I finish with that. Let me remind you about integral closure. So what we need, if you have a, I don't even actually need this. Let me skip it because let's go straight to transcendental extensions. Okay, so transcendental extensions are opposite of algebraic. So suppose you have a you have a claim. You have X inside the field K, and K containing K small is an extension. We don't know if it is finite or not, just extension. Then either, and in fact I stated that once, I think K yeah, so maybe I should use notation. Okay, K Z and Z is any element. Then either Z is algebraic, or K contains the field of rational functions. It was in the first lecture, in fact, but I can repeat it. Okay, if there exists a polynomial P with coefficients in K small, such that P of Z equals 0, then Z is algebraic. Otherwise, the map from K of T to K big, so otherwise, this map is injective. Okay, and then K contains a field of rational functions, because it's a fraction field of this ring. If you have embedded certain ring into a field, then you embed the fraction field of this into the same ring. Okay, there's essentially nothing to prove, and we had that already. There's another trivial lemma. It's really trivial lemma, like completely trivial, but I gave its proof just for completeness. So if you have a finite extension, then you have a finite extension of rational functions. So lemma, if you have k over k finite, then k of t over k small of t also finite. And it is easiest to see just by tensor product. So you have k of t is k small of t multiplied over k small with k big. And this is finite dimensional over k of t over k small with k small. This is finite dimension. And for this isomorphism, you can use primitive theorem. I mean, you can prove it different ways. So the easiest, the simplest way is to use to state it. To state the proof is to use theorem of primitive elements. That this is a primitive extension. So k big is k small of alpha, where alpha is a root of certain polynomial, and then k big of t is k small of alpha, where you added also t. Do you have any questions about this? There's essentially nothing to prove in that. So if you are sort of thinking what is we are proving here, you're right. We don't prove anything. It's trivial. But if it's not obvious to you, you have to have the proof. Should I explain it in more detail? Okay. No one? Let's go on. Now there's this important notion of, do you have in, transcendency basis. It's a bit like basis, but for algebraic dependency. So we have to start with defining algebraic, like how you define the basis. It's a maximal subset of linearly independent vectors. So algebraically independent definition, if you have k over k small extension, you have z1 dot 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 zn inside k big elements. You say that they are algebraically independent over k small if there's no algebraic relations between. In other words, you have an embedding of rational functions. So you have k small of z1 dot zn rational functions are embedded to k. This means that you have no polynomials which vanish in this z. Then you have again, like we had there, you had a map, injective map from polynomials to k big, and this gives you a map from the corresponding fraction fields, which are rational functions. Yeah, also this is the corresponding extension. is called purely transcendental. So you have k of z1 dot zn over k small, called purely transcendental. By algebraic independent elements. So this means that this is so extension is purely transcendental if and only if k if this is k big is just rational functions. So it's a field of fractions on the algebraic variety Cn. Since not all we didn't prove it, but it's true that not all algebraic varieties are birational equivalent. This means that non-L extensions are purely transcendental. So the field, it keeps information about birational type of algebraic variety, because what is birational equivalence is precisely the equivalence between the corresponding fraction fields. Okay. Yeah, now transcendence basis. It's an important notion. So definition, you have z1 dot zn. I can have like, but let's keep it finite. Inside the k big, algebraically independent, and then suppose that k big over the k small, and then you write rational functions z1 dot zn is algebraic. I remind you that algebraic extension is one which all elements are algebraic. It's not really finite, because things like algebraic closure of Q are algebraic, but all elements are algebraic. Okay, then z1 dot zn is called transcendence basis. It's actually a good exercise to prove that the number of elements is independent from the choice. It's very similar to how you prove for the basis in linear algebra, that if you have two bases, they have the same number of elements. You just somehow do it by induction by the number of elements in the basis. I'm not going to prove or to use that transcendental dimension, the number of elements in the base of transcendence, is invariant, but it is true. Any questions? Okay. Okay, but the important thing that I told you, that this I gave you a precaution that this extension is algebraic. It's not necessarily finite. However, this is not true for algebraic varieties. So for algebraic varieties, everything is really finite. So let's prove it. So theorem. I think I used at some point, but maybe not. I don't remember. So you have k of x, field of rational functions, of fractions, on algebraic variety, affine variety. And then yeah, T1 dot Tn generators of OX. And then you have a certain subset. You can take this subset in T or anywhere else. So T1 dot Tk is a maximal algebraically independent subset. So it's really transcendency basis, because the rest of the elements are algebraically expressed through this. So this is basis of transcendence. Then you have an extension k of x over k, and now this is the algebraic independence, so you have rational functions here, t1 dot tk. This is finite. Okay, and proof is very easy. So the idea is that so to have something where you have lots of algebraic dependence, you have to have something which is not finitely generated. So we have let's use induction. Use induction by n. So by induction, I can already assume that k of x intersected with subfield generated by t1 dot tn minus 1 is already finite. Is finite over this k of t1, no, sorry, tk here, of t1 dot tk. So we have rational functions here. And by induction, I mean, this, if you have a algebraic variety, it is quotient, the corresponding ring is a quotient of C t1 dot t1 dot tn by some polynomial equations, p1 dot pk. Then you have a subring here, which is generated by the first k elements, and then you take the quotient not by all elements, but ones which belong to this subring. So this is again a quotient by an ideal, and this is a ring of algebraic functions on some other algebraic variety, which in fact just projection. But anyway, so you have this this other algebraic variety, and you prove that everything for it, and then you use induction by n. So you can assume that this is already finite. Now we have an alternative that you have k. Let's denote this subfield. The corresponding subring by x1 is corresponding subring. Well, OX1, corresponding subring. And x1 will be the corresponding quotient variety. Okay, and then you have k of x1. This is algebraic over k of t1 dot tk. This is finite. This by induction. But then you have k, you have OX1 is obtained by adding O of x, and then you, O of x is obtained by O of 1 adding, well, like, I write here Tn, but this is not polynomials. This is subring generated by Tn. So this is subring generated by Tn, considered as a function on x. So it's a ring generated over OX1. And this implies that k of x is tk of x1 when you added t, and here you add it in the sense that either it is transcendental and then you add rational functions, or it's algebraic and you just add it. If it's algebraic, we are done. And if it's a transcendental function, then t is independent algebraically from t1 dot tk, which is impossible by our assumptions. So only this scenario might happen. So this means that t is algebraic, and being algebraic, it generates a finite subfield. Okay, I think now we can have a break. Let's have a break until 31. We have like precisely 5 minutes. 14:31, we're back. If you have questions, you can ask. Really important application that there is a birational theory of algebraic varieties. This is a theory of category of varieties where morphisms are birational equivalents, and it is a theory of fraction fields of algebraic varieties. But now what we see is that fraction fields of algebraic varieties are the same as finite extensions of just rational functions. So essentially, the birational theory is just Galois theory for such finite extensions. What I didn't prove yet, that any such extension is a fraction field for some algebraic variety. It's not hard, and it's left for you as an exercise. There is indeed a bijection between finite extensions and fraction fields of algebraic varieties. It's not hard, and in fact, we shall be closer. We're getting closer to the statement anyway, so maybe I will even prove it. Okay. So what we proved here is that essentially, if you have like dominant projection to dominant finite projection to Cn, this is more or less the same as transcendental basis. So now I will prove it more formally. So this is this statement. So you have again an algebraic variety, and you have a set of coordinates. Then this gives you a projection. You can just so projection is forgetting of certain coordinates. This is something we have discussed, but let me write it somewhere. So if you have a map Cn to Cn minus k projection, or Ck projection to T1 dot Tk, the corresponding embedding is C of T1 dot Tk embedded to Cn. Now we have certain variety. You can do 2C_T1 dot Tn. Sorry. The opposite. I mean, the direction is opposite. Now, if you have x, which is quotient of C T1 dot Tk Tn by P, then projection, it's a restriction of this map. So it is a map, it takes OX. I denote it by Pk, it's projection to the first k element. And it's again a map from a certain subvariety here to our x. So Pk star maps or x intersected with this ring, C T1 dot Tk, quotient by P intersected, this is our ideal, C T1 dot Tk, and this is embedded into in the polynomials. C of T1 dot T, well, to the quotient, so it's embedded to OX. This is how the projection works. It just projection is forgetful map. You had certain functions. Now you forget about all functions which are dependent on n. Because if you look at here, this is all functions. These functions which are independent on the last variable. Okay. This is how I explained how projection works. So this is more or less tautology, so there's nothing to prove. It's a definition of projection in that setup, in that category. Of course, if you really look how projection works, geometrically is different. Because geometrically, the image of projection is not necessarily a affine subvariety. It's possible to see how it can be non-affine subvariety, for instance. Well, you can do it. It's not hard. So we just define projection as it's here. And well, sometimes it corresponds to the geometric side, sometimes not. And we shall see when it corresponds, we shall use it. But when it doesn't, you can't use it because it's just wrong. Okay, so this is projection. So now proposition. You have x inside Cn, affine subvariety. Now you can have projection x to Pk to Ck, projection map written here. And then there are two things which are equivalent. So it's projection to the first. Oops, sorry. What happens? Okay, so first, Pk is dominant, and dominant to here, to this, to Ck, and the extension, you have the ring of fraction, the field of fractions over the sub-ring generated by its the coordinates, rational functions. A priori, this is not even an embedding, but it is dominant, then it makes sense. Is finite. And the second is that T1 dot Tk is transcended by this. Is transcendence basis in K of x. And the proof, again, there is nothing, essentially nothing to prove, so it's again trivial, but let's do it. So proof. Okay, so suppose it's a transience basis. Then this is definitely a subring in K of x, because it's they're algebraically independent. So if T1 dot Tk are transience basis, then C of T1 dot Tk is embedded into Ox, and then the corresponding map of polynomials T1 dot Tk to Ox is injective. This precisely that this is dominant. And then it is finite, as we just proved. Finite by, is it called theorem 1? Yeah, it's by theorem 1. So we proved that this implies this, and the converse is completely trivial because, okay, if this is finite, this first, if this is subfield, they are algebraically independent, but then if this is finite, this means that it is maximal algebraically independent subset, so the converse is trivial. Trivial by definition. Okay. Now what I'm going to do is, okay, so what we had is that this is in a sense almost like a finite map. In fact, you shall see that there, for appropriate projection, so you can slightly change these coordinates and it will be a finite map. The projection will be a finite map. So this is how we work, why we are doing what we are doing. We are trying to build finite maps which are projection. And this is a version of, the simplest version of Noether lemma. It just says that every algebraic variety admits a projection to Cn. Okay, so let's look again on this situation described in this proposition. So you have a projection map x to Ck. But then all elements f inside Ox are algebraic over Ck. And this means that they're satisfy polynomial equations. So Tk plus 1 and so on, T up to Tn satisfy polynomial equations. Okay, but let's, for instance, take a projection, take Tn. So Tn, there is a polynomial equations P of T1 dot T n minus 1, and then say T, such that P of Tn, I plug Tn in the last, is equal 0 on, so let's do it like that. You have a polynomial P inside Ox of T. Ox, sorry, because it depends only on the first variables, it will be Ox1 of T, where x1 is just projection of x to n minus 1 coordinates. So it's a sub-ring which depends on first n minus 1 variables. You have it because you can express algebraically nth variable from the rest. They have an algebraic dependence. It won't be finite unless this polynomial is monic. So this is finite. This is something we know, if and only if. what is finite? I consider x as projected to x1, and this map, it is finite if and only if P is monic. Because what is O of x? It's O of x1, where you added one more variable. And then we know where addition of one more variable is finite as a model over the smallest string, if and only if the monic polynomial is polynomial with leading term 1. So maybe, yeah, it's something I should have done earlier. So let's see it. Integral closure. So you have, there's nothing here, unfortunately. So let me just tell it to you. All right. Yeah, so if you have variety x projected to y, this means that OY is mapped onto OX, and OX is finitely generated as OY model. This is equivalent for some notoriety, but this is more or less equivalent if and only if all f inside OX are roots of monic polynomials. This is an observation we did several times, and I'm going to use it a lot. And monic is t power n plus sum from I equal n minus, well, I equals 0 to n minus 1, ai t power I. So monic is polynomial with a leading term 1. Okay. So the idea now is that somehow we can modify the projection by just doing linear transform. And doing that, we shall have another coordinates where everything is okay and the corresponding polynomial is monic. So let's do it. So theorem. You have x inside Cn. You have t, it's now z, I think. Yeah, it's now z. z1 dot zk is transcendence basis. And now we have a projection map. So we have p n minus 1 from x to x1, projection map. Okay, and O x minus 1 is denoted, sorry, the image of this map, O of x1 is denoted by A. So this is notation. Now I'm interested in dependence, how Zn depends on the basis, which is z1 dot zk. And I claim that for appropriate change, it becomes finite. So finitely, so Zn is a root of monic polynomial on z1 prime dot zk prime. Well, do we take all of them or just? Right, where zi prime is the same as sum. Zi prime, sorry, is the same as zi plus lambda I zn. and the lambda I are generic. Generic in the sense that they don't, well, I pick sufficiently generic one, which means that I pick one outside of some union of subvariety. In fact, it's outside of a certain subvariety. In this sense, generic. Okay. So now I'm going to prove that. So this was assumptions. Let's do step one. I pick a polynomial P of z1 dot zk t, a polynomial such that P of t is equal of zn is equal 0. It exists because zn is algebraically dependent. It's algebraic over the ring, the field of fractions, C of z1 dot zk. So you can always have such a polynomial. If there is not such polynomial, then you can add this polynomial to this field, and you'll obtain a subfield of bigger transience degree in or in the field of fractions on K, which is impossible. So you really have an algebraic polynomial. Then I will write it as a sum. Now I will do something. I will consider it as a polynomial on all variables, including z. So it was and f of z1 dot zn is a biggest degree homogeneous polynomial component in P. So it's of course we can think of this polynomial as polynomial one variable, where the rest of the variables sit in OX. On the other hand, we can represent it by a polynomial on all variables, from z1 to zk and then zn. And I pick P such that f has smallest degree. A priori, I mean, it's the map from polynomials to OX is not injective. So you have a choice here. But we choose it in such a way that the homogeneous part is the smallest, of course, non-zero, and smallest possible degree. Now I will, it was still step one. Now let's go to step two. I would do something with this homogeneous thing. Namely, I would consider a new homogeneous polynomial obtained from the first one by a linear change. Yeah. So Q of z1 prime dot zk prime zn is f of our expression. So z1 plus lambda 1 zn, z2 plus lambda 2 zn, and so on, zn. Okay, I would evaluate this polynomial at a point 0, 0, 0, 1. Q of 0, 0, 0, 1 is not equal 0 for lambda generic, because Q of 0 dot 0 dot 1 is equal to our f of lambda 1, lambda 2 dot lambda n 1, lambda k 1. This is a homogeneous polynomial. If it is 0 for all these values, is just identically 0. This cannot be because it's assumed to be non-zero. So generic now, in that sense that it is non-zero. This is the only condition we need for genericity, and this is just you have this second dimension one condition in the space of parameters, and we just want our lambda to be outside of the set of zeros of this polynomial. Set of zeros is measure zero set, so it's okay. It's a closed, nowhere dense subset. Okay, now I claim that then, under this choice of lambda, we shall already have our polynomial is monic. So this was step 2. The step 3. In these coordinates, P 0, 0, 1 is non-zero. In fact, leading term is also non-zero. Has degree, the same degree as f. So it's the biggest degree in of all monomials here. So we have non-zero coefficient under the biggest degree of the last term. Then this P is, so we can now express P from Z1 dot Zk, and T is monic on T. We're done. Because this is what we needed, right? What we needed is that the coefficients under the biggest power of T is non-zero, and we have it. So the rest, so there are two ways of looking at degree of this polynomial. This is something slightly misleading. When we start, we look only on degree under T. And when we end up, we also need the degree under T. And then we looked at homogeneous degree, which is degree of all variables added together. But of course, one of the degrees is bigger than another. So if you have a non-zero terms in T power D, it's a maximal degree term in both senses. So it's really maximal degree term also as for T dependence. Yeah. Okay. Now we can, in fact, prove the Noether, at least one version. But in fact, when I was preparing today's lecture, I found that there's no, if you just look Google, normalization, lemma and normalization, there's nowhere normalization in there. And I don't know why they don't include the other, which I will tell next time, version of Noether normalization lemma, which has normalization. But this is sort of canonical in all current textbooks, which are found on Google. I think in older literature, there was explanation why this Noether normalization lemma is related to normalization. Now, there's no relation in all anywhere. But yeah, first, let me give you a trivial observation, which we had like a million times now, that if you have three models, like A, three rings, A contained in B, contained in C, and B is finitely generated as A model, and C is finitely generated as B model, then C is finitely generated as A model. Okay? Should I explain this? We had it lots of time. The idea is that, okay, take generators of B over C, take generators of C over B, and then express these generators in terms of generators over A using generators of B. Okay. Now what we have is that our projection map P from x to x1 is finite, where x1 is the image. I mean, it's something we have discussed. It's a subset in Cn minus 1. Use induction and use this. So this proves that composition of finite maps is finite. And this is finite because of this argument. We express the extra variable as monic polynomial on the rest of the variables. Okay, so taking composition, and applying this using induction by n, we obtain the Noether, the less useful version, but it's still useful, version of Noether normalization lemma. Normalization lemma. If you have x inside Cn, and well, should we do something? No, here we don't. Then there exists a finite dominant projection, linear, obviously, projection x to C power d, where d is, of course, transience degree of x. I'm done. If you have any questions, I didn't read your yesterday's homework yet, but I will. I think Monday we can discuss it. And if you have any questions, please ask. Otherwise, I'm done for today. Next time, before I'm finished, who of you know the homotopy lifting lemma? Okay, because I would need it at some point, and should I take the whole lecture by homotopies and coverings? Okay. Then I would take less than whole lecture, but you can ask questions, and of course there's a lot of literature. Just Google, look at Wikipedia, and so on. But we shall definitely use some of it. And of course, look at Riemann surfaces of functions, because this is what is this about. So just take any complex analysis textbook, Riemann surfaces, and look at Riemann surface of a function.